Hey everyone, my name is Yudo. I'm working as Solutions Architect at Amazon Web Services, and we are really glad to have you all joining our sessions today. This particular session is going to talk about how we can optimize the cost of our machine learning pipeline running on AWS, whether that is from the TCO or total cost of ownership perspective or the running cost perspective also. These are the key takeaways that I hope we can all learn today. Did you know that SageMaker's pod instance can potentially help you to save up to 90% of the compute cost for the model training? Also, did you know that we can leverage SageMaker Elastic Inference to give us up to 75% savings for our inference costs? And what if I tell you that we can potentially condense all of our models or some of our models into one serving instance instead of multiple instances, and we get to pay for less. So we can have multiple models in one instance as long as they share the same serving container. So let's get started. Let's begin with how we can do data ingestion that is cost optimized, and how we can cost optimize the cost of data labeling, and how we can also cost optimize the process of training our model and also the tuning. And before that, we have the data processing. And finally, we need to cost optimize the model inference as well. This is how a typical machine learning pipeline looks like. People can start by collecting data, labeling data, and doing some pre-processing on the data. Then the data science team can start doing some prototyping and research work to determine the right algorithm for the machine learning model. And then the model will be trained to get the best prediction result, as well as to do the hyperparameter tuning to get even better prediction result. And finally, the model can be deployed for real-time inference or batch inference. And there's some tools that people usually use to do workflow to facilitate the pipeline. They can use Kubeflow, Apache Airflow, or AWS Step Functions. All are supported on AWS. Let's learn how we can cost optimize the data ingestion pipeline. Imagine that you have data sitting on your relational database. It could be on MySQL, PostgreSQL, Oracle, SQL Server, or Aurora. Then you need to get all this data to be loaded on your data lake on Amazon S3 with some transformation job in between, and everything needs to be happen automatically. Then you can use AWS Glue, which is a serverless ETL service that allows you to write your own PySpark script to actually ingest and transform the data and load it to Amazon S3. And this glue is being built according to the duration of the job run. There is a minimum of 10 minutes if you're running if you're running a PySpark script, or if you have your own development endpoint, and a minimum of 1 minute if you're running a simple Python shell script. So with Amazon or with AWS Glue, you're able to do some transformation and ingestion of the data in a serverless way. Alternatively, you can also leverage spot instances with Amazon EMR or Elastic MapReduce that allows you to have a cluster of instances running Spark jobs. And you can also do the same to actually transform and ingest the data into your data lake. Spot instance is easy to instance that is unused and are available for the lower price than the on-demand price. And for the data lake itself, you can save costs by leveraging the tiering mechanism in Amazon S3. In Amazon S3, you can store your infrequently accessed data, probably older data, and push it into the lower tier. Lower tier means they are usually infrequently accessed and the storage cost is cheaper, all the way to the archival. So if those data are really unlikely to be accessed anymore, you can actually archive it to get the lowest storage cost. Now that we get our data loaded to Amazon S3, we will look how we can further optimize the cost for the data labeling, especially if you run supervised machine learning. Imagine that you have some raw data that you need to get labeled by your own private workforce, by vendor managed workforce, or even Amazon Mechanical Turk. You can use SageMaker Ground Truth to orchestrate all the process. And even better, if you choose, you can enable the active learning that is able to do some automatic data labeling. How the active learning works is by grabbing some sample of your raw data and then make them available to the workforce to be labeled. After the resulted label data is out, it will use that to improve the active learning model so that it can auto-label other data samples. If the auto-label result is good with high confidence, that will be used so that you can save costs on some human data labeling. Otherwise, it will be made available again to the workforce for further labeling. This process happens repeatedly until all your data is labeled, allowing you to save the cost. And you can save cost by up to 70% for data labeling. This SageMaker Ground Truth is currently supporting image classification for single label, semantic segmentation, bounding box, and text classification. Now that we have had our data label, we'll look at how we can further cost optimize our machine learning pipeline, especially on the data processing and model training, as well as tuning. Before we get our hands dirty by doing all the cool data science stuff, probably you want to take a look into some set of AWS AI services. And the purpose is that so that we can save some cost that we need to run the development, like finding the right algorithms, doing some prototyping, research, and even running the machine learning training. That could be a significant cost. So you can potentially just leverage some AWS AI services that provide some functionalities by default. These services are available as top of the machine learning stack on AWS, like Amazon Recognition for doing face detection, image recognition, and also video analysis. There is also Amazon Poly for doing speech synthesis or text-to-speech. There is Transcribe for doing transcription, Translate for doing translation, Lex for building chatbot, and also there is one for natural language processing that's called Amazon Comprehend. And there are many others. For example, Amazon Personalized to build a recommendation engine for your e-commerce, for example, and that uses collaborative filtering. There is also Amazon Fraud Detector to do some fraud detection. And there is one more that's called Amazon Text Track for text track for extracting the text, and even one more which is Amazon Forecast for doing forecasting. All right, if none of the AI services are actually meeting our needs, we can still build our own custom model and run the training ourselves. And how people typically do it is that they will start small, probably with an EC2 instance or a small SageMaker GPU Notebook instance to do some prototyping or research to find the right algorithm done by their data science team. And this instance is typically always running or probably is always on during the working hours. And we don't need much of CPU or RAM for this kind of activities. And as we get more ready into productions, you realize that, hey, I need to run more data processing. And these processings usually take larger RAM or memory. So probably what you need to do is to resize the instance to get the instance that has higher memory. Okay, that's fine. But now the data processing probably only happens for 1 hour during a day, while your instance is probably left running during working hours or even all the time, 24/7. And then as you need to do model training, you realize that, hey, I need GPU. I need to resize my instance into the one that supports GPU. For example, NVIDIA Tesla V100 that is supported on AWS. All right. Now what happens is, this is a typical usage profile for a working day of a data science team. Orange shows activities of doing prototyping and research that requires smaller vCPU and RAM. Red shows data processing that requires more memory and only happens for 1 hour. Blue shows the training job that requires GPU that is coupled with higher vCPU and RAM, especially for NVIDIA Tesla V100. So we use P3.2x large that can cover everything. And this, unfortunately, may result in potential around $32 unnecessary cost. Why? Because we provision for peak, not only when we need to run the job, but all the day, probably during the working hours. So this is an anti-pattern. This is an anti-pattern because we run different activities that require different resources on an always running box in the same box. So what would be the better way? The better way is to run different activities that require different resources in different machines and only get built when the job is running. For this, you can use SageMaker on AWS. For example, your data science team can use smaller ML.T2x large instance to run the Jupyter Notebook for prototyping during the working hours. When the data processing is needed, your data science team or the machine learning pipeline can spin up SageMaker Processing job that uses ML.R5 large or X large that is optimized for memory only for 1 hour when you need the processing to run and only be built for that 1 hour. When you need GPU to run the model training, you can use ML.P32.X large that supports NVIDIA Tesla V100 only for 2 hours and only be built for that 2 hours only. This is a typical SageMaker notebook. So with this SageMaker notebook, you can spin up an EC2 instance right from AWS console, and that EC2 instance will have the Jupyter Notebook installed by SageMaker. SageMaker will give you the URL so that you can pass it to your data science team for them to access it right from the browser to do some prototyping and research work. And these are some good recommendation or best practices for doing prototyping on the notebook. First, you need to start and stop the instance when or only when you need it. So when you're off the working hours, you can actually stop the instance right from the AWS console. Or even better, you can actually script it as well. And it is also good practice to always start small. So you need to experiment with smaller data sets. And if that experiment actually yields good results, only then you can experiment with a larger dataset, or you can run the actual training with a larger dataset. So start small with the smaller datasets for experiments. Now, we probably need to run some data cleaning or data pre-processing. How can I do it on AWS? You can use SageMaker Processing to run data cleaning or data pre-processing as part of the machine learning pipeline or on demand. If you look at the sample code here that is on Python that is using SageMaker SDK, you can see that you just need to specify the Docker image location that has the environment that you need to run the job. For example, Apache Spark in this case. And then you need to define what instance type that you need. You need to define the location of the input data in Amazon S3 and the location of the output data. And then you just simply call the method run. And what's going to happen in the background is that SageMaker Processing will spin up an EC2 instance. It will download the Docker image and run it on that EC2 instance. It will copy the input data from S3 into the container, run the processing job, and upload the result back to S3. And you only get to pay for the duration when the processing job is actually running. That is about processing. Before we get into the custom model training, make sure that you have all that you need, which is people and time. We can potentially lower the total cost of ownership, especially on the cost of development, data labeling, or research. By leveraging things that are already available to us, provided by vendors in AWS Marketplace, like models, data, or algorithms. For example, say that you want to build a custom NLP model, natural language processing, to support specific language. And you find that in AWS AI services, that language is not yet supported. Instead of having to collect thousands of documents as training data that support that specific language, you can potentially just look at AWS Marketplace and see whether there's any model, data available for you to actually save some development costs. AWS Marketplace at the moment covers various categories such as natural language processing, text or object detections, and also text classification, and many others. And if nothing actually suits your needs from AWS Marketplace, you still can potentially lower your TCO down by cutting on the effort of development by leveraging algorithms available on SageMaker. We have SageMaker Autopilot and also SageMaker built-in algorithm. SageMaker Autopilot is capable of doing binary and multi-class classification, regression, for several use cases, such as risk assessment, price prediction, and churn prediction. For other use cases, such as image classification, object detection, topic modeling, and many others, you can potentially use SageMaker built-in algorithms. All right. Now, if you really have to run your own training job for your own custom-built machine learning model, then you can leverage SageMaker Training Job that uses per second billing to actually save on some compute costs. If you look at the code sample here that is written in Python that uses TensorFlow with SageMaker SDK, you can clearly see that you can use a pre-built container that has TensorFlow. So instead of having to build your custom Docker container or Docker image, you can just leverage the pre-built container by SageMaker that has TensorFlow, and you just need to specify which version you want. And then you need to specify what's the instance type, whether that's GPU or not, how many instances you need, and you need to upload the training code, the .py file that has your method that should be run when you need to train the job, the model. And all you need to do is just to call the feed method, and in the background, SageMaker Training Job will spin up an EC2 instance, download the Docker image that has the TensorFlow in this case, and then inject the training code that you uploaded into that container, download the data from S3, and then run the training job and upload the result to S3. And then it will terminate itself after the job is done, so that you only pay whenever the job is running to save some compute cost. If you look at it on the screen, you can just change one parameter to make your SageMaker SDK to deploy the training job in your local machine, in your laptop. And the purpose is so that you can quickly test on smaller datasets for an experiment or a new algorithm or new parameters, so you can get the result quickly and save on compute cost. This is called SageMaker Local Mode. Right, if you look at the code here, you can see that just by adding some parameters that are related to Spot, you can get SageMaker SDK to request Spot instance on your behalf, and then run the training on Spot instances. And again, Spot instances are EC2 instances that are unused, so that they are available for lower price than on-demand instances. Probably some of you have questioned. I heard that Spot instances can get interrupted because they are based on supply and demand. What if I have a training job that needs 100 epochs, and on the epochs 99 it just gets interrupted? Do I need to start over from zero again? If you use SageMaker checkpointing mechanism, you can resume the training job where you left off. And the way it works is that on your training code, you need to save the temporary model into specific location, specific path, and then SageMaker will actually handle the data periodic upload to Amazon S3, so that whenever the Spot instance gets interrupted and the training halts, it can resume again once the Spot instance comes back from where it left off. It can download the temporary model from S3 and resume again. And with spot instance, you can potentially save on compute cost by up to 90%. In my personal experience, I used to run training job on SageMaker with spot instance in North Virginia region, and my spot instance were not interrupted for 12 hours. Alright, another way to further cost optimize our training job is by using the pipe mode. There are two ways we can get our data to be downloaded from S3 into the running container that runs the training job. File mode or pipe mode. Using pipe mode, SageMaker will actually stream the data directly from S3 into the running container, so that your training job doesn't have to wait until all data or full data be loaded first before it can start the job. This has benefit. First, your training job can start more quickly. Secondly, your I/O throughput will be higher. And then the third thing is that you will have higher processing capacity as well. And this will translate into lower costs because the overall training time will be quicker, so the cost will be less as well. It's also important to actually right size the instances that we use for data processing or training. It is important to pick the right instance type with the right size, and the way we can do it is by looking at CloudWatch metrics on CPU, GPU, memory, and disk utilization. Or we can do our own benchmarking as well to actually compare the instance type and size to give the best training time and the prediction result. And it's also recommended to always pick the latest generation of instance, for example, M5 instead of M4, because the newer are always cheaper or more performant, or both. So it will be always better to pick the latest generation instances. And the third thing that you need to do is that you need to start small, and then if you need more resources, you can actually scale out first, get more instances, and then you can scale up as necessary. Hyperparameters matter when we run machine learning training, especially on deep learning. Things like optimizer, mini batch size, and other parameters can really affect the quality of the predictions. And finding the right hyperparameter value can potentially eat up the valuable time of our data science team because it involves trial and errors that can actually be automated using SageMaker Hyperparameter Tuning. Using SageMaker Hyperparameter Tuning, you can actually save on the total cost of ownership by allocating your data science team to focus on what really matters to them and leave things that can be automated with the automated hyperparameter tuning job. And it also supports early stopping so that when a training doesn't really perform well for initial epoch, it will stop the training before it gives you some extra cost, unnecessary cost of extending the training into more epochs. And another thing is that you can leverage the warm start that is supported in hyperparameter tuning in SageMaker so that one tuning job can actually make use of the knowledge of previous tuning job to make the hyperparameter finding more efficient. At the moment, hyperparameter tuning job supports multiple algorithms, including your own custom algorithm. That is surely a lot. But let's get into this almost final section about how we can optimize the cost of model inference. 90% of the cost is driven by hosting our model for prediction, and 10% is coming from training, and 90% is significant. And we need to drive this cost down. And there are several features that we can leverage to actually optimize this cost of model hosting. For example, by leveraging the SageMaker endpoint that supports auto-scaling for real time, or we can use the SageMaker batch transform for transformation or prediction in batches, or we can use elastic inference that allows us to attach GPU accelerator into smaller EC2 instances that normally don't have GPU, or we can use SageMaker Neo that allows us to compile our model. We can also run multiple models into the same instances as long as they run the same serving container using SageMaker multimodal endpoints. And you can also benefit from adopting the serverless model by using AWS Lambda and store the machine learning model in EFS, which is Elastic File System. Now we have an example on PyTorch. In this code sample, you see that you can load a model into this SageMaker SDK and then get it to be deployed in real-time SageMaker endpoint. And you can also deploy model that you train somewhere else, not in SageMaker, like probably in EC2 or even outside of AWS. And likewise, if you train your model in SageMaker, you can also deploy it in EC2 or even AWS Lambda or even your own on-premise server. So there's no lock-in here. So after you call the deploy method in this particular code, SageMaker will spin up EC2 instance with the right size that you request and inject the Docker container and run the Docker container that has the serving code for PyTorch or TensorFlow. And then it will download the model from S3 and serve the predictions through a URL. Speaking of TensorFlow and PyTorch, there are several other frameworks that are also supported in AWS SageMaker. It is also important to take a look into our CloudWatch metrics and use the data to pick the right instance type and the right size to host our model in SageMaker. And it's also good to always pick the latest generation instance. If you have multiple models that needs the same serving container, you can actually run them in the same EC2 instance to save you some cost of having to deploy multiple instances. This is called SageMaker multimodal endpoint. And your client code, when calls the prediction, they need to specify which model that it wants to talk to. Imagine a use case where you need to run a prediction for your clients and the traffic pattern is non-uniform. Probably in the morning, there are less traffic. When it gets to noon or afternoon, there are more traffic and it reaches the peak and then it goes down again. Instead of having to pay for multiple instances to handle for the peak, while you don't actually have that traffic all the time, you can actually save costs by using SageMaker Endpoint Autoscaling to get the number of EC2 instances auto-scaled based on the number of invocations that happen per instance, or you can use other metrics as well. And if you ever need to run training job that requires GPU, you'll probably have taken a look into this table. You need to choose the EC2 instance type that has GPU. For example, P3 instances that has the NVIDIA Tesla V100 that is coupled with higher vCPU and RAM. Or you can choose G4 instances that has NVIDIA T4 GPU with less CPU and RAM that is more optimized for inference. What if I need even less, but I still need the GPU, but I need less CPU and RAM? The answer will be to use SageMaker Elastic Inference that allows you to use normal EC2 instance size, probably smaller EC2 instance size that normally don't have GPU, and then you attach GPU accelerated right into it so that you have GPU in that instance. And this can potentially lower our inference cost by up to 75%. Now, what if I don't need GPU for my inference? And what if the traffic is quite low or it's quite bursty? Most of the time, there's no traffic, it's idle, but sometimes there are traffic. You can potentially benefit from adopting the serverless model with AWS Lambda and API Gateway. With AWS Lambda, you can upload your Python code or code in other languages and get the Lambda to run the code whenever it gets triggered. For example, when there's a prediction call. And then with the recent integration from Lambda to EFS, you can store your machine learning model in EFS file system and get it mounted to the AWS Lambda function. So now you can have a prediction architecture that can save on the compute cost because you don't pay when they are idle. There is a part in the machine learning pipeline whereby you probably want to do some data preprocessing to remove noise or bias, or get inferences from large datasets, or to run inference when persistent endpoint is not needed. which is asynchronous, or you want to do some interpretation post-inference. For this kind of use cases, likely you don't need an instance that's always running. So you can use SageMaker Batch Transform that can give you some compute capacity whenever you need on demand or as part of the machine learning job, and only be built according to the duration of the job run. So today we have learned how we can use SageMaker Spot instances to save up to 90% of model training costs. We also learned how we can use elastic inference to save up to 75% on inference costs. And we know how we can combine multiple models into one EC2 instance for inference, so long as they share the same serving container. And there are many more points that we have learned today. That's all we can learn today about how we can optimize the cost of running our machine learning pipeline from the TCO perspective and also from the running cost perspective. In order to improve your confidence or hands-on experience with AWS, you can visit or access the digital training built by experts, or attend the instructor-led class by qualified AWS instructors, and learn how to design, deploy, and operate highly available, cost-optimized, and secure applications on AWS. Please do take your time to fill up the survey because we want to understand what topics or what services that you want to know more about. Let us know what you think, and thank you very much.